A point charge creates an electric field that permeates all space. At a position r in this space, the electric field E of r is given in SI units by the expression 1 over 4 pi epsilon, with epsilon being the permittivity, times q being the charge, divided by the magnitude of the separation vector r minus r prime, to the power of 3, times this separation vector itself. This is simply Coulomb's force law, only omitting the charge on which that field acts at the point of interest. The cube dependence of the denominator comes about because it includes the 1 on distance square dependence of Coulomb's law and also normalizes the vector r minus r prime to create a unit vector that identifies the direction of the field at the point of interest. Implicit in electromagnetism and its theoretical foundation, the Maxwell equations, is the principle of linear superposition. This principle states that the net electric field of several point charges is the linear vector sum of the individual field vectors. By applying the principle of linear superposition, the electric field of multiple point charges can be calculated, according to the expression shown here. The net electric field is then the vector sum of the field vector associated with each point charge Qi. This slide presents an example problem in 2 dimensions. In the xy plane measured in meters, 2 point charges Qi and Q2 are placed at a location of 0, 2 and 2, 2. Qi has a charge magnitude of 20 microcoulomb and Q2 is equal to 30 microcoulomb. The expressions for the individual field vectors are given on the right. In order to determine the net electric field E of r at the point of interest 1, 5, the individual fields have to be calculated and added according to the principle of linear superposition. In order to determine this net electric field, first, the vectors that identify the distance of separation between source charge Q and point of interest are calculated. They are r minus r1 and r minus r2. The results are minus 1, 5 and minus 1, 3. Since the denominator of the expression for the net electric field contains the magnitude of these 2 vectors, the 2 magnitudes are also calculated as the square root of 26 and the square root of 10, respectively. Substituting these results in the expression for the net electric field at r, and using a convenient approximation for the permittivity of vacuum, which is approximately equal to 1 on 36 pi times 10 to the minus 9 farad on meters, the result is obtained. The electric field at the position 1, 5 is given by the vector that has an x component of minus 9.9 and a y component of 32.1 in units of kilovolts per meter. The magnitude of this vector is 33.5 kilovolts per meter, and it points in the direction of 11 o'clock at the point 1, 5. A good strategy for solving problems like this is to first draw a sketch of the situation, including all the charges that create the electric field. Then work out the difference vectors between those charges and the point of interest for each of those charges, then the magnitude of those vectors. Finally, add all the information together in a large sum and calculate the electric field. This is a similar problem. A charge of 10 microcoulomb is located at a position with an x-coordinate of 2 and a y-coordinate of 2 also. A 20 microcoulomb charge is located at 0,3. As before, the length unit is meter. The task is to determine the electric field at the point of interest 4,4. Following the strategy outlined a moment ago, the first step to the solution is a sketch. Since both charges are positive and to the left of the point of interest, it can be expected that the electric field vector points towards the right, maybe in the direction of 2 o'clock. In step 2, the vectors that identify the distance of separation between the source charge and the point of interest are calculated. They are 2, 2 and 4, 1 respectively. In step 3, the magnitudes of these two vectors are calculated. They are square root 8 and square root 17. Applying the principle of linear superposition, the two individual field vectors are added vectorially. Finally, after some algebra, the result is obtained. The electric field vector at the point 4, 4 has an x component of 18.2 and a y component of 10.5 kilovolts per meter. This means the x component is almost twice as long as the y component. This is consistent with the expectation that saw this field vector pointing in the direction of about 2 o'clock. In this problem in 3 dimensions, four equal charges Q of 10 microcoulomb are positioned on the xy axis at a distance of 3 meters from the origin. The net electric field is to be determined at a position of 4 on the z-axis. The z-axis comes out of the plane. The net electric field vector can therefore be expected to point at us. As before, first the vectors r minus ri are calculated. 4 different vectors are obtained. All 4 vectors have the same magnitude, and the term r minus ri, magnitude to the power of 3, is equal to 125. Applying the principle of linear superposition and substituting gives the result that is shown here. The electric field vector at the coordinates 0, 0, 4 points upwards in the z direction, as expected. It is interesting to consider what electrostatic force may act on a fifth point charge, for example Q equals 20 microcoulomb, that is placed at the point of interest. This in fact represents the standard problem of electrostatic. Determine the force on a test charge, in this case Q equals 20 microcoulomb, that is created by a field of source charges, in this case these 4 charges in the xy plane. Multiplying the test charge according to Q test times E gives the force of 0.23 Newton at the point of interest at the position 4 meters from the origin on the z-axis. Problems like this can only be mastered by attempting them oneself, going through the calculation using a pen and a piece of paper, doing all the steps and obtaining the result. And then doing the same again, maybe with a slightly different configuration, changing the charge magnitude, changing the position. That sort of experience is required to master problems like this.